Having considered how atoms hybridize their orbitals to bond, I thought it may be interesting for us to look at how they now bond together. So let's spend a bit of time looking now at molecular orbital theory. So when we looked at hybridization, we considered how individual atoms can change their atomic orbitals to produce hybrid orbitals, allowing more bonds to form. So for example, carbon in methane hybridizes its orbitals to form sp3 hybrid orbitals by mixing its 2s and its 3 2p orbitals together. Boron can form sp2 hybrid orbitals, and carbon can also form sp hybrid orbitals in CO2, where carbon forms two single or sigma bonds and is also able to form two pi bonds with another atom or two. So the hybridization allows us to explain the shape of the bonds around each of those atoms, but it doesn't explain how atoms now come together and combine their orbitals to form molecules. So in the same way that atomic orbitals interfere with each other either constructively or deconstructively to form hybrid orbitals, when we combine these orbitals to form bonds, they will do the same in order to form molecular orbitals. And molecular orbitals are either labelled sigma, pi or delta. Sigma and pi we've met before. Sigma is what would be known as a single bond. Pi is when we have a double bond. And delta we may meet later on in this series of videos. So let's consider a simplest example that we can think of, and that is two hydrogen atoms coming together to form a covalent bond. Each have an electron in their 1s orbital, and their 1s orbital is obviously a sphere. No hybridization is necessary for them to do this, so there will be two possible outcomes when these two come together. So let's look at those two possible outcomes. Our first possibility is that both our s orbitals are in the same phase as each other. So again, if we consider them to be a wave, you can see they would both be in the same phase, like so. So if they're in the same phase, they will combine together and we will have constructive interference. So here we've shown the two coming together, and in the middle where they've overlapped, they are interfering with each other constructively because they were both in the same phase. And this results in a new molecular orbital being formed. So we no longer consider hydrogen H2 to have two 1s orbitals combined. We now have a sigma bonding orbital which contains the two electrons, one from each of our hydrogen atom. And we have had constructive interference, and our sigma bonding orbital is at a lower energy than the two original 1s orbitals. The other outcome is that we have deconstructive interference, where one is in a positive phase, as we have here, but the other s orbital is in a negative phase. So you can see here and here, these are in different phases to each other. If that's the case, constructive interference occurs, and we will have what we call a node. So that's where we don't have any electron density in that region. When this happens, we say that we again form a sigma molecular orbital, but it's an anti-bonding orbital. We don't want to have electrons in an anti-bonding orbital because that would result in weaker bonding between the two atoms. So we don't have, as you can see, for hydrogen, we don't have any electrons because both were already used up when we formed our bonding sigma orbital. But in the same way, when we looked at hybrid orbitals, if we start with two atomic orbitals, we will have two hybrid orbitals formed. In a similar way, in forming H2, we've started with two atomic orbitals, and therefore we will form two molecular orbitals. And in an anti-bonding orbital, there is no electron density between the two nuclei. So that's a summary of what we have learned so far. when we've looked at how H2 is formed, that we either have constructive interference, which leads to a bonding orbital, or deconstructive interference, which will lead to an antibonding orbital. And this is the result of those two coming together. We start with one electron in each of our atomic orbitals, and they will combine molecular orbitals here. Once these formed, these no longer exist. They've gone. We now have formed a molecular bonding orbital, a sigma, and an anti-bonding orbital, which luckily for hydrogen does not contain any electrons. We can also label them. So our first molecular orbital we call 1 sigma, and our second, the anti, is 2 sigma, but we put a star next to it to indicate it's an anti-bonding orbital. So we can also consider, in a very similar manner, what happens when two helium atoms should try to combine together. So again, we will form a molecular bonding orbital and an anti-bonding orbital. However, now we have 2 electrons from helium atom A and 2 electrons from helium atom B. So they combine, and I will have 2 electrons in my bonding orbital and 2 electrons in my anti-bonding orbital. And when we look at the difference in energy of these, this energy difference is larger than this energy difference. So this force, in terms of pulling the atoms apart, is greater than this, which is trying to bond the atoms together. And hence we know He2 will not form. And we can write our molecular orbital electronic configurations as well. So for H2, it's just 1 sigma 2. For He2, should it ever form, it would be 1 sigma 2, 2 sigma star 2. And obviously that would show anybody that it could not exist. So that was the first part of our introduction to molecular orbital theory. Hopefully you found that interesting, just extending what we've done so far on hybrid orbitals, and hopefully just takes you a little bit further from what you've learnt at A level.